All right, you guys, today we are looking at the law of cosines. So first thing I'm doing is I'm giving you a little recap of the law of sines and when we can use it. So first off, I can use the law of sines if I know an angle with an opposite side. So here in my first visual, right, two angles in one side. So with the markings, we have two angles and the non-included side. So this is an example of angle, side. But over here we have two angles and the included side. So this would be ASA. So again, law of sines works when we know one angle with an opposite side. So for example, in my first instance, here I have the angle of 56. The side opposite is 12. Here I have an angle of 67. The side opposite is what I can solve for right now. Okay, in the second visual, I have angle, side, angle. So here, the side that I know, I actually don't know the angle right here, but I can solve for it. So I should always fill in that missing third angle first. And we can always do that. If we know two angles, we know the third one as well. We know that the sum of all three angles in any triangle would add to 180. So here, if I add these two measures up, I have 117. So the supplement of 117 is 63. And once I have that measure in place, I can solve for this side opposite this angle, or this side opposite this angle. It doesn't matter. I'll just label this one as the first one to solve for. All right, the other time that we can use the law of sines is when we have two sides and one angle that is opposite one of the sides. So we call this the non-included angle. And as we've called it before, we call it side-side angle. And when we first learned about side-side angle, we remembered that, oh, it has the potential for that swinging door, right? It could suffer from that swinging door effect. So to remind you of this visual, right, we know that it has the potential for where B is, where B could be the hinge in between the two marked sides, where this side could swing into a second position, making a very different looking triangle with the same given information. Okay, it does not always happen that way, but it does sometimes happen that way, and we call that the ambiguous case of the law of sines. So here I'm giving you two visuals. They're both side-side angle. So the angle that I can solve for has to be opposite one of the marked sides. So here I have an angle, side opposite. Side, here's the angle opposite. I can solve for this one. I'll call it X. Okay, in this one I have an angle. Here's the side opposite. Here is the side. Here would be the angle opposite. This is what I can solve for. All right. So one of these is ambiguous and one of them is not. So it's a matter of where would the hinge be if it is. So my hinge would be here if it's ambiguous. And right here if this one is ambiguous. All right, so what I'm picturing when I think, is it ambiguous or not, I'm looking at the side that is opposite the marked angle. Okay, and I'm looking at how it relates to the other side. So in this case, the 4 is bigger than the 3.5. So if this is my hinge, and this is 4, it's bigger than this side here, it really has no alternate position to swing into to maintain that 58-degree pathway. So this first one is not ambiguous. Right, so process of elimination, this one must be ambiguous. So here is my hinge, and when I look at the side right here, 6, opposite the marked angle, I see that here it's smaller than my other side right here. So that means where that hinges, this side can flap, it can swing into an alternate position about right here. Let me show you that with my compass. So here I have my compass setting to this side right here. So right here is my hinge. So if I swing that 6 over here, I see it makes contact right in here, right here, and it makes another triangle with that same information that looks a whole lot different, right? It would swing into this location right here, where this measure right here would be 6 also. So my triangle could look like how I drew it initially, but my triangle could also look like this with the same information. So here, this one is ambiguous. And to be clear, let me add a little side note. We know that ambiguous only occurs with side-side angle. When the side opposite the given angle is smaller. I have to emphasize smaller a couple of times, so smaller than the other given side. Right, that swinging door, that side of 6 is small enough to swing into a second location. Let me add that detail. So the side is small enough to swing into a second location. And it creates two very different looking triangles. So this first one, not ambiguous, that 4 was too big to swing into a second position and maintain that 58-degree pathway. But in this one, the 6 was small enough to swing right here and make a second looking triangle with the same given information. So that's what we mean by ambiguous, right? There's two very different looking triangles that could have the same information. All right, so next up, well, what would happen then if you know two sides and the included angle? So let's make ourselves a picture. So let's say that I draw a triangle like this. Let's say I tell you that this side is 5, and this is 6, and this is 72. So what happens here? Do we have an angle with a side opposite? We don't. Right here we had just side angle side. We do not have an angle with the side opposite. We get stuck. Right? Again, to use the law of sines, we need an angle with an opposite side. All right, so to use the law of sines, let me slide this up. We need an angle with an opposite side. All right, so then what's our solution? Do we have another option? Oh, we sure do. We have the law of cosines. So just like the law of sines, we have a proof to back up this new theorem. And I made a short little video to show you the proof for the law of cosines as well, if you are interested. Just like the law of sines, we're really proving this new relationship using our basic right triangle trigonometry, SOHCAHTOA. All right, so in this one here, I want you to have eyes on one angle. We're going to look at A, and the opposite side, lowercase a. All right, so here is our new structure. We have A squared is equal to B squared plus C squared minus 2 times B times C times cosine A. I know it looks like a beast. It's not that complicated once you start working your way through it. So keep in mind that we are either solving for one of these two pieces. We are either solving for an unknown side or we're solving for an unknown angle. And those are always in opposite positions, right? These are in opposite positions. And B and C are simply the other two sides. Okay, so now I want to show you how it's used. So I'm going to show you how it's used before we do a big example. All right, so we can use the law of cosines to solve a triangle. So solve a triangle just means find all the missing parts. So we can use the law of cosines. Let me slide it to here. If we're solving a triangle that has two sides and the included angle marked. So if we have side, angle, side. So in this instance, so I'm looking at the one angle that's marked, and I can solve for the side opposite. I'm going to call it x. All right, so let me just transfer that law of cosines right down here so you can see the structure. So a squared equals b squared plus c squared minus 2 times b times c times cosine a. So I'm solving for an unknown side, so I'm solving for the A part right here. I'm going to call it x. So x squared equals. So the B and C are just the other two sides. It doesn't matter the order I put it in. So I'll say 7 squared plus 8 squared minus 2 times 7 times 8 times cosine 57. Now what's beautiful about that is that I can actually type all of that into my calculator. So keep in mind that x right here is the unknown side. So once I type all of this into my calculator, I'm really just solving for x by taking the square root. Right? I'm not going to carry it through to solving it fully. I just want to talk you through what you're actually solving for. So we can solve for that unknown side that's opposite the marked angle. Okay, I could also use the law of cosines if I have three sides marked. So side, side, side. All right, I could pick any of these angles, but let's say that I pick this one right here. So keep in mind that the angle that I have marked x is opposite the side that's marked 5. So I'm going to do the same thing. I'm just going to lay out the structure. It helps it sink in as well. So a squared equals b squared plus c squared minus 2 times b times c times cosine a. So what's different here is that I'm solving for the unknown angle. So the unknown angle x is opposite the side of 5. So I put the 5 right here. So 5 squared. And the 5 is the side opposite angle x. Right, the one that I'm actually solving for. All right, so 5 squared equals, well, the other two sides are 6 and 7. The order that I plug in does not matter. So 6 squared plus 7 squared minus 2 times 6 times 7 times cosine x. Right, that's what I want. I want the x. That's the unknown angle. All right, and then from this point, it's really just an algebra problem where I'm working to isolate that unknown. All right, let's do two big examples on the flip side. So go ahead and flip your sheet over. And here we go. So in example 1, I want to solve for x in the triangle below. All right, so what do I have marked, right? I have side, angle, side. So we are given side, angle, side. Let me lay out my structure. So I know a squared equals b squared plus c squared minus 2 times b times c times cosine a. So I'm solving for x, an unknown side, so that goes in right here. So x squared equals, well, my other sides are 8 and 14. Again, the order, it does not matter. So 8 squared plus 14 squared minus 2 times 8 times 14 times cosine 50. Okay, all of that I can plug into my calculator, so watch me do that right now. All right, so I have 8 squared plus 14 squared minus 2 times 8 times 14 times cosine 50. All right, so I have x squared is about, I'm still going 4 decimal spots, so 116.0156. And then all I'm doing here is I'm solving by taking the square root. So square root of each side. So if I build off of what's in my calculator, this will be more precise. So I can say take the square root, so second x squared if you're using a calculator like mine, second answer, and it builds off that previous answer, that's fine. I would get 10.7718, and if I built off of the rounded intermediate step like I've been showing you, I could say square root 116.0156, and I get the same thing, so it worked out nice. So building off of rounded intermediate steps, or building off of what was stored in our calculator more precisely, we got the same rounded answer. Now technically x squared, when I take the square root, I should get plus or minus 10.7711, but obviously we're only looking at the positive, so positive 10.7711. And that is our missing side. All right, we got one more, and it's a bigger example. Here we're looking at getting all of the missing angle measures in triangle HAT. So what we're given to start is we're given just the 3 sides. We're given no angles. Okay, so this is similar to when we just say solve the triangle. And if we say solve the triangle, we're really just saying, well, find all of the missing parts. So fill in all of the missing information. All right, so first we got to pick an angle. So I'm just going to pick one. So I'll say step 1, let's find the measure of angle H. We're going to use the law of cosines. All right, so step 1, let's pick one angle measure. Let's solve for the measure of H. So H is opposite the 10 right here. So when I look at my structure, let me lay it out. So a squared equals b squared plus c squared minus 2 times b times c times cosine a. All right, so what am I plugging in? So the measure of H is what I want, and that's opposite the 10. So I have 10 squared right here is equal to, well, 5 squared plus 10 squared, right? The order I put them doesn't matter, minus 2 times 5 times 10 times cosine, I'll call it H, right there. All right, so now it becomes an algebra problem. So here I have 100 is equal to 25 plus, oops, I put a 10. I meant to put a 12. Let me fix that. The other two sides were 12. Okay, let me back up and fix that detail first. Let me explain what I did wrong. All right, so the h was opposite the 10. The other two sides were 5 and 12, so I just misread that. So I have the 10 squared, that's opposite the h that I want. The other two sides were 5 and 12. All right, so good fix. So 25 plus 144 is 169. And then here, this is a product, so that comes as a package. So I'm multiplying out the 2, the 5, and the 12, and that gets 120. So minus 120 times cosine h. Okay, I cannot combine these. They're not like terms. Right here, this is a product. So I cannot combine. I need to isolate this part right here. I want to get that cosine h all by itself. So I want to take away the 169. So I have negative 69 is equal to negative 120 times cosine h. All right, from here again, I'm trying to get that cosine h all by itself. So I can divide away the negative 120. And that's going to leave me with, let me crunch it. So I have a negative 69 divided by a negative 120. So I know a negative over a negative is going to give me a positive, and my ratio is 0.575. So cosine h equals 0.575. Well, I want the angle measure, so I'm going to say the inverse of cosine with that ratio, 0.575, is going to give me the angle measure as an approximation. So second cosine, 0.575, that's going to get me a measure of about 54.9004. So 54.9004. That's the measure of h. So measure of h is about 54.9004 degrees. Let me put that in place right here. So 54.9004 degrees. All right, so now I need another angle, doesn't matter which one. Let's say the measure of A. So step 2, let's find the measure of A. Okay, so to get the measure of A, well, I realize, well, I have an angle now with a side opposite. So I don't need to use the law of cosines again. I can now use the law of sines. Right? That's easier. It's a little easier formula to use, and we can only use it when we have an angle with a side opposite. Okay, so I want the measure of A. So I can say that sine A is to the side opposite 5, just as sine 54.9004 is to 10. All right, so I've built my proportion using the law of sines. So now I cross multiply. So 10 times sine A equals 5 times sine 54.9004. And then I'm just dividing away the 10. So sine A will be approximately, let me type that in. So here I'm looking at, slide that over, 5 times sine 54.9004. And then I'm going to divide that by 10. All right, so my ratio is about 0.4091. So 0.4091. And now I'm going to go ahead and take the inverse of sine with that ratio, 0.4091, and it's going to give me the angle measure. So second sine, 0.4091, and I get an angle measure of about 24.1483 degrees. So that's the measure of angle A. So 24.1483 degrees. Let me add that to my picture. So here, 24.1483 degrees. All right, so that first angle, I had to use the law of cosines because I just had 3 sides. Once I found that one angle, now I had an angle with the side opposite. I could use the law of sines. It's easier. And now if I want that third angle, remember, well, we have 2 of the 3 interior angles. They have to add up to 180. So my last step to get that last angle, as I'm finding the measure of angle T, right, I just have to remember that all interior angles of a triangle add to 180. So all interior angles in a triangle add to 180 degrees. So all I have to do here is, well, I can take 180 and I can subtract the 59.9004 and the 24.1483, and then I'm left with my answer. All right, here we go. So 180, okay, take away the 54.9004 and the 24.1483. Okay, I'm left with 100 degrees, 0.9513. So 100.9513 degrees. And that would be the measure of T. All right, let me slide that over. All right, so again, law of cosines first. We found a missing angle. Once we had that angle, we had an angle with the side opposite, law of sines. Okay, and then once we have 2 angles in a triangle, we know that all of those angles have to add to 180. So we take that 180 and deduct the 2 measures that we know. What we're left with is the measure of T. All right, have a good rest of your day.